you will know everything today. The webinar is live, but it will be also recorded, and in a couple of weeks, it will also be available on the YouTube channel of ESRF. If you have a question, you can start typing them in the question and answer box, but we will answer to them only at the end. And please, Daniele, the floor is yours.
Thank you, Adriana. Can you hear me well?
Yes.
Okay. So I'm gonna share my screen. And I suppose you can well see the slides.
Yes, everything is fine.
Okay.
Thank you very much.
Okay. So thank you, Adriana, for a kind introduction. And as you said, I'm gonna give you an overview of the new ID29, a bit, let's say, how we started the project, what are the characteristics of the Beamline, and show you some example of possible application, and also to show how it's possible to access the Beamline, how to apply, and what kind of experiment can be done at ID29. So let's start with room temperature crystallography. There's been a sort of resurrecting enthusiasm towards room temperature crystallography during the last year. And this is because there have been very different studies that they show that room temperature crystallography has the power to reveal more physiologically relevant conformation that can be hidden at when working at cryogenic temperature, both because of the lower temperature that selects a certain conformation, but also because sometimes the presence of cryoprotectant can hinder the access to catalytic pocket of active sites of the protein. This is also a certain importance for the development of new therapeutic agents and also to do it a new strategy for ligand binding that can be done directly in crystals slurry at room temperature. So getting the ligand diffusing inside the protein, inside the room temperature crystals without doing any pre-soaking and cryo trapping. Because of course, the presence of radiation damage, serial crystallography is one of the best strategy that can be applied to obtain room temperature structure. Of course, when we talk about serial crystallography, we think originally to the pioneeristic experiment that were done at the free electron laser. And this kind of experiment also contributed to revamp this interested in towards room temperature crystallography. So in this kind of experiment, you know that there is a stream of crystals with this sent in front of the free electron laser pulses, and every time that the beam intercepts crystals, a diffraction pattern is produced, and that can be then index integrated and scaled relative to the error in order to reconstruct the relative space. Thanks to the high brilliance of the free electron laser beam, also this kind of study gave origin to what the kind of experiment that is commonly known now as diffraction before diffraction, and opened the possibility to study crystal size that were so small that it was unthinkable to measure before. And because of the time structure of the beam, open also new perspective for doing a new kind of time resolved study that was not possible before. The fact of working at room temperature and on microcrystals in the context of time resolved study open also new perspective for do more efficient on the probe experiment when using proteins that are naturally photoactivatable, or a protein that contains photoactivable ligand, which could be a natural substrate of the protein, or an artificially chemically synthesized compound that contain a photocleavable cage. In this way, thanks to this limited crystal size, it's going to be possible to activate the whole volume of the crystals, or at least the largest fraction of the volume of the crystals, in order to get a more homogeneous distribution of that of the activated conformation inside the protein when we are collecting data. On the same way, when working with microcrystal, thanks to the most advantageous, let's say, surface over volume ratio that the microcrystal has, when we are doing ligand mixing, is it possible to get a faster and more efficient ligand diffusion inside the microcrystals, and then, of course, open the possibility to do new kind of drug binding studies, or also doing in Cristallo directly enzymatic reaction. On top of that, when we look at how fast our biological process and how fast is an average enzyme, we see that most of the enzymes are mainly active in the micro to millisecond time range, which was clearly a time speed that was not achievable using all the third generation synchrotron, but with the advent of fourth generation synchrotron that allows to get a much higher increase in flux density of what we can get at the sample position, it opens new perspective to perform time resolution study in the micro to the millisecond time regime. And it's basically with this target in mind that we have designed the ID29 optical setup. So the past, or say, or the origin of this ID29 upgrade project, they date back almost, it's scary to say, almost about 10 years ago, because it was in 2016 that we had the first idea, and we started getting the first scientific cases to build a crystallography beamline that could fully profit of the characteristic of the new EBS machine. And it was that at that time that we produced the first conceptual design report that was all outlining what kind of performance that we were looking to have with the new beamline. It took then a couple of years to get a complete details technical design and to assess the technical feasibility of this beamline design that we were going to make, and with the plan to start the construction and the procurement phase during the SRF shutdown that we had in 2019. Of course, during this time, one thing that came up that created a little delay in our planning and disrupted the operation of everyone worldwide, and the life of everyone worldwide was covered in 2020, which was the time that we were supposed to start the extra hatch construction and get most of the components for the beamline being delivered. Nevertheless, we could cope with these difficulties, and in 2021 and 2022, we start the assembly and the commissioning of the optics and experimental hatch, respectively, and we could welcome the first user experiment at the end of 2022. And now, when in 2023 that just concludes, we could achieve the full user operation. The full user operation, and indeed also we integrating new features that were not available last year, like the new laser and the new deployment for the acquisition system. For what concerned the X-ray sources, so ID29 used to have and still has an in-vacuum U21 undulator, which is the one with which we have initiated the operation, which, thanks to the characteristic of the extremely brilliant source machine, gave us again an influx or gain in brilliance compared to the previous to the old beamline by a factor of 10. But then the design of the optics has allowed us to boost up the flux density at the sample position by 4 or 5 order of magnitude. In the meantime, during last year, we also have installed the new generation of the undulator, the permanent magnet cryo-cooled undulator, the CPMU 16, which we are currently commissioning, which is going to also help us to boost even more the flux that we're going to have at the sample position and extend, as you see, the operation energy. So this is a bit of a layout of the whole beamline. We have the 2 optic hatches that are in the old experimental hall, or in the main experimental hall, while the beamline end station, the control cabin, are built in the new shot froze hall, the new building extension that was built during the first phase of the SRF upgrade. We have both the hatches and the sample preparation lab that are controlled in temperature, humidity, And here you have just a quick glance of the experimental setup on the end station with the diffractometer and the detector that you will see in a minute and a few slides. So the lab is fully equipped for users. We have different facility, and we have also the possibility for users to come before the experiment at the Beamline to test their sample preparation offline. And we have other things that should be coming in the near future, which is also the possibility to have a more protected environment for working with light-sensitive samples and for with oxygen-sensitive sample. So as I said, the optical layout has been specifically designed to fully profit of the characteristic of the new EBS machine. And one of the things that we made was to build a new kind of monochromator, which is already used for this other kind of application, but specifically designed in this case for ID29, which is based on a double multi-layer system, which we operate at a typical bandwidth of 1%. Which is about 100 times larger than what usually is done on macromolecular crystallography beamlines. So the fact of operating with 1% bandwidth has the double advantage of thickening the UL sphere, so which is important when we're working with still images, because in this case, since we don't rock the crystal, they're gonna produce diffraction spots that are larger, so more complete than what you will have in normal still oscillation with normal still images with a smaller bandwidth, and increase the flux that we're going to deliver the sample position. And higher flux means lower exposure time, so better time resolution. By design, this kind of monochromator, despite the fact that it sits at 70 meters from the sample, it's extremely stable in the energy resolution, and what is also important for beam stability in the angular range, so the beam doesn't move over the time in spectra and in position. The second hatch is basically the home of the timing system that we have implemented. So the hatch contains two choppers. The first chopper is what we call the heat load chopper, which removes a lot of the heat and produces, as you see here, 90 microsecond pulses, which is positioned upstream to a fast chopper, which is a very fast rotating motor, which allow us to produce pulses that are as long as 10 microseconds. Both systems, they have a very low jitter. We have less than 1 microsecond jitter just with operating with the heat load, and better than 100 nanosecond when we use the fast chopper. Normally, we operate at the repetition rate of 231.25 Hertz, which is a direct division of the main frequency of 925. And as I said, the heat load chopper produces constantly 90 microsecond pulses, while with the fast chopper, thanks to the profile that you see here, this graded profile, by offsetting it, we can either produce 10, 20, or 30 microsecond X-ray pulses. This kind of profile, it shows the intensity of the beam, and it's quite interesting to see that these glitches that you see over here are not noise, but rather are the bunches, the single bunches in the hybrid mode of the filling ring of the rings that we see passing by. So this is an overview of the whole experimental setup. As I said, so we have a double chopper system that produces down to 10 microsecond pulses. We have a new integrating detector, which is the Jungfrau 4M, which has been developed for free electron laser application by PSI, so originally for Swissfel, which is a detector that is able to cope with the very high flux density that we deliver at the sample. We have a newly developed micro diffractometer, which is LMD3 UP SSX, which contains a very high speed fast translating motor, which can run synchronously with the choppers, with the pulse beam that is produced by the chopper, and can adapt different sample delivery system, which could be either fixed target or injector based, or some more exotic one, as you will see in a few slides. And we are currently integrating a nanosecond laser to be able to do light activated pump and probe kind of experiment using light activation. So this is a closer view of the experimental setup. So on this big vessel here, we have the KB focus and mirror. The beam is focused down, the beam size about 4x2 micron that you see here on the scintillating material with a lot of fluorescence around from the screen. Sample position is over here. Here it's mounted a fixed target, and we have recently moved the Jungfrau for M detector on its final movable table that allow us to get it as close as 10 centimeters for the sample, which means that for at the standard energy we get better than 1.6 angstrom resolution on the edges. And here you see the effect of having such a strong beam on a scintillating material that it's even melts a bit. So we need to replace it constantly. How a diffraction pattern looks like when we have a beam with such different characteristics. Basically, this is, you see, it's still images with a very well diffracting crystals where we could see all the spots. I could say that this matches pretty much what we were simulating initially when we were making the Beamline design. You see that the fact of working on 1% is still far away from lower diffraction conditions. So we don't see the classic lower diffraction pattern with multiple lunes. But we see that the spots, they look a little bit elongated. And this is the effects of both the bandwidth and the fact that we have a high demagnification of the beam in order to focus it down at such a small spot size. But this is actually, in this case, is not actually an effect, a defect, but it's rather an advantage because they also contributes to get more full Bragg spots being recorded, even if we don't have any rotation. So for what concerns the sample delivery methods, we have the mainly used one, the mostly used one, and also it's the simplest that we always use to test sample when we have new samples, is based on a fixed target. So this, in this case, the sample slurry can either be mounted on a foil, be sandwiches between two mylar foil, like in this way, or in like in DLS silicon chip, where the crystals are sitting in a well-organized well-organized pattern that you will see now in the middle in this movie. What happened in both cases, the diffraction, the data collection scheme is exactly the same. So we continuously scan, usually using a zigzag scan. But the fact that the pulses are lower, are shorter than the repetition rate, basically we shot only in front of the holes when is the silicon chip, like the one that you see in the video down here. When we are on the foil, basically we have sort of free geometry, so we can decide how frequently to shoot, so how often to sample the scanning area. On a support like that, this doesn't consume a lot sample at all, because it's enough to load 3 up to 5 microliter of crystal slurry. And out of support of this size, we usually collect 240,000 images with the spacing of 20 by 20 micron. And as I said, this is a very successful system to be used to do pre-screening. And this is how it looks like in the MS-Cube interface. You see that you have the crystal slurry, which is distributed everywhere, and then we scan on this area. The other systems are based on high viscosity extruders. So we have both a few available of the Beamline, but we can also accommodate the one that are brought by the users. So they are either high viscosity, as you say, as you see here in the picture, and this is in the view from MS-Cube. We can also accommodate the Serialix, that is this flow cell device developed by Göteborg University, which is very easy to set up and to operate. And the typical media that we use for this kind of injector are ADA-LCP for membrane protein, but also hydroxyethyl cellulose and grease. And as I mentioned before, the sample preparation lab is equipped to do the sample pre-preparation And also we have an offline bench with injector that can be used for to pre-test the mix and the flow of the injector without having to be at the beeline. On top of that, we can also accommodate, of course, with a little bit of preparation in advance, some new user-developed devices like other kind of flow cell, microfluidic chips, or also acoustic levitator. The other sample delivery methods that we use is the tape drive system that has been developed by the Lübeck Technical University. So in this case, you have this conveyor belt where the crystals are dispensed using this 3D printed mixing nozzle that we got developed from CFEL. In this case, the crystal slurry is injected on the tape and can even, since there are two channels, it can even be mixed with a ligand in order to follow the ligand mixing process directly. By offsetting the distance between the position point and the X-ray position, then we can play with time delay. Clearly, this is not a device that is suitable for faster time reaction, but a rather slow time reaction. But we have very recently successfully used it both for some example of light activation that we will see later, and also in some ligand binding study that you see. This is how the density of the ligand is building up in the electrodensity map. For what concern light data acquisition, we have a new data acquisition library which has been developed at the SRF, which is called Lima2, which is able to cope with the high data rate. And one recent development that we have is that it can identify on the fly if the images contain diffraction. And we flag directly in the HDF5 files if the image contains a diffraction. And here you see this is basically the content of the HDF5 files with all the frames. And it indicates in these plots how many diffraction spots have been identified for each frame. Based on that, we can do a pre-selection and only process the data that only process the frame that are above a certain threshold. On top of that, Lima also produces a virtual powder diffraction pattern, accumulating all the images that are identified as hits. And also more recently, since last month, we produce a second one which contains all the images that are not considered hits, not as a hit, so that we can validate if this selection process was successful enough. We are also currently working on implementing some automatic pipeline to carry on the data processing downstream taken from this image selection. And here, just I'm going to show you how good the electron density map it can be. And this is, for example, it's a globin structure collected with a 10 microsecond pulses, and you see that the whole heme configuration is completely preserved even after that exposure. As I said, we are completing at the moment the installation of the nanosecond laser, which was one of the things that was mostly delayed, unfortunately, because of some technical issues initially. So we have at the moment two ways of focusing down the laser, either by using a parabolic mirror system. So you have the X-ray which is coming from here, and then we have laser which is focused down by the parabolic mirror system on this side, or a lens system, which is this is a view from top. So you have the X-ray which is going here, and the laser which is shined from this side. And we are currently also working for a more final solution, which is in collaboration with the MBL by using directly the on-axis viewer, so to be able to do the injection directly from the camera or from the optics that does the sample view. Now I'm gonna just go quickly to a couple of nice user case stories that was collected during the last year of population. So the first one is from the group of Jose Martin Garcia of the protein NQ01 with a fat-dependent oxidoreductase, which is involved in many critical mechanisms and is a potential target for tumor treatment. And in particular, it's in particular involved in the kinome metabolism by doing a 2-electron reduction, avoiding the formation of semi-kinome. This is a very interesting target, not only for, of course, for biomedical application, but also as a time resolved target because of the cycle of its mechanism. So the part of the study was focusing on this part. So was the reduction with of NADH oxidation, and this was the first structure where it was possible to observe at room temperature the presence of the NAD bead bound in the pocket cell of the active site that you see here, and the structure revealed the structure determined at room temperature. They revealed also some cooperative, anti-cooperative mechanism between the two active sites of the dimer, and this is, of course, is considered a good starting point for future time resolved study. The other project is a project from the group of Mario Smits from the University of Wisconsin, and it's concerned phytochrome photocycle, and in particular the structure of the phytochrome, which is a red light photoreceptor which is present in plants, and it's one of the biggest known enzyme which is controlled by light. So upon light exposure, the chromophore that it's contained in the phytochrome goes to an isomerization of this D ring that you see here, and has been suggested to trigger a quite important structural changes. So in this case, we made a quite more exotic experiment by using the tape drive system. So we were depositing the crystals on the tape, and then we were making the crystal travel across a laser spot size before going to intercept the X-ray, the X-ray beam. And we got a few different experiments, also to do some control experiment to show that we were not producing any artifact, and that all the results were genuine. And basically, you see in this different electron density map difference that we have structural changes, which is induced in this chromophore, which combines with the transition between the two isoform of between the Z and the D conformation, and these are his electron density map of the new conformation. And this had opened the possibility to interpret this movement, which is quite interesting because it between these two conformationally, it goes from beta sheet to alpha helix is a secondary structure. So we at the moment, as I said, we started the operation at the end of 2022. At the moment, we are doing the Beamline allocation mainly via the bag system. At the moment, we have 14 bag proposals that are running on ID29. So the next deadline for submission for a bag proposal is the 4th of March. We also have the possibility to do rolling proposals, but this is going to give access only to a single experiment as it's designed by the rolling system. But I can say that the last bag meeting, we started to have discussion to open the access to the Beamline via traditional bags application, where users can ask for a few shifts for 29 to initiate some room temperature time resolved studies on their project. There is one thing also that is important, is that the amount of data that we produced, and it's part of our mission, is not only to collect data, but also to offer the possibility to users to process data. So these are, I keep track of the amount of data that was collected in overall user experiment until last summer. So it's quite outdated, but you see that in 26 experiments that we got in the first six semester of 2023, we got almost 1.4 petabytes of data being collected. So that kind of since the amount of data that is produced is too large to be exported, with also supported of European Open Science Cloud. We have developed a system which is called the Visa, where the users can log in from their lab, create a virtual machine using the SRF cluster, and then from there to process the data. So just to resume in a simple nutshell, with the new 29, we have completely new beam characteristics that open the way to do new kind of experiment. We have pulse beam operation at the repetition rate of 231 hertz. And we operate with pulse length of 90 microseconds, which can be trimmed down to 30, 20, and 10 microseconds by using the fast chopper. We have a photon flux as a sample, which is around 310 to the 15 photo per second, which gives you, it's 100 to 1,000 times brighter than what you can achieve on standard MX Beamline, which we do expect to at least double with the operation of the permanently cryo-cooled ondulator. So just to thank a lot of people that have been contributed to this project. So we have now a mailing list where you can contact all the people that are working on 29. So in particular, Shibom, Julien, and Samuel, in addition to myself. A lot of people in the XRF structural biology group, and all the different groups, support groups and development groups at the SRF. I want also to thank the user, Jose Marius and Tech for the experiment. And as I said, the tape drive is a development from the Lübeck Technical University, in particular Mia and Leaf were quite busy during the initial experiment with the tape drive. And with that, I almost done. I just want to advertise the EMBO practical course that we are going to have here on site on the second week of July. The deadline for the application is on the 15th of April. You can check the program on the EMBO webpage or by flashing this QR code. It's quite an intense hands-on practical course where we are going to train participants in all possible aspects of from sample preparation to data collection to data processing. And also, I want to remind you that the next webinar of this series that is going to be focused on structural biology beamlines is going to be given by Igor Menikov, who is going to present ID30A3, and this is going to be on the 20th of June at 2 p.m. And with that, I thank you for your attention, and I hope that I'm still online.
Indeed, you are online.
Okay.
Thank you very much. A virtual round of applause. And you've been perfectly on time. If you would like to write your question in the question and answer. While people are writing, I have one question. In your new Beamline, you have a extremely nice diffraction diffraction maps, and the maps was looking like being 1.8, 1.9 by eye. And I'm really amazed by this, by the high resolution at with these very tiny crystals. So does it mean that the smaller is better?
Not necessary, because of course what you present are always the best at diffracting cases. It really depends on the sample preparation. You know, a crystal is a crystal, whether it's smaller or big. For sure, what we don't have in this kind of measurements are possible additional defects which are added by cryocooling or by cryoprotectant. But we have seen cases of nice small crystals not diffracting, as we have seen cases of ugly crystals diffracting very well. So if crystallography is always crystallography.
The aleatory part of it. There is one question. So how long does it take to install the tape drive? How easy would it be to switch between fixed target and tape drive?
So the installation of the tape drive doesn't take very long. I would say between half an hour and 1 hour. One of the critical part of the operation is the crystal dispensing on the tape drive. So the optimization of that part might take a little bit longer. That's why one of the things that we usually do, it's before going to the tape drive, we ask to check the crystals on the fixed target, so we make sure that we have a decent diffraction. I also have to say that we have a very nice new dispensing system that overcomes some of the problem that we have encountered in the past, because crystal slurry can have crystals that are a little bit sticky, and they might tend to settle a bit. So we have a system that allow us to overcome some of this problem. Yeah. Then depends, of course, what happen is, of course, is that with the tape drive, the heat rate it's very much smaller than what you can get in fixed target, because by dispensing the crystal slurry on the tape, you effectively dilute it.
Another question, would you suggest this approach for enzyme inhibitor complexes when they do not work as expected in classical co-crystallization experiments, when you don't see the whole inhibitor in the active site when with the normal crystallography?
Absolutely, yes. So the case of the Jose Martin, I show you, it was one of the cases that didn't work on in cryo condition, but it did work room temperature. And I have to say that once that you have the crystal slurry, mixing with the ligand and collecting, it's a matter of minutes. So absolutely, yes. Also because in this way, we can also be a little bit more, we can work at higher concentration of the ligand. And given the fact that diffusion in the microcrystal is more effective, we can screen different concentration much quicker. Yeah.
One thing which is really on the volume of your slurry, because it seems that in your fixed target you have a volume of a few microliters, but how much if you are going to put it on your tape?
So for the tape, it should be at least, I would say, between 100 and 200 microliter, yeah, at least. Then depends many things by many things, because, for example, in this kind of example, these are three different time points. So this means that the amount of crystals that you need, it's at least 3 times what you would need for a single experiment. So in that case, you need to have more. That's why assessing the diffraction capability initially, it gives you a better idea of how well is behaving your samples and how what you can expect by setting up a more complex experiment, like with the tape drive. Yeah. Also depends, of course, by the symmetry of the crystal.
That was my next question.
Yeah. Yeah, depends.
Are you still going towards higher symmetries like P6 or?
I mean, we have been having a little bit of everything from P1 to H32. So it really depends. Of course, if you have like a low symmetry space group, then you need to accumulate many more hits before stopping the data collection and move it to the next sample.
There's another question. Did you try tachography method on this beamline? Did it work?
No, we didn't. Yeah.
Which could be the advantage of tachography on
I'm not an
time
expert,
result?
so I don't know if I'm completely ignorant on the subject. So, but I don't I don't know if with the Bing characteristics that we have, with the high divergence that we have, if this is applicable. But I might be completely wrong. So,
if I'm not wrong, there is a beamline for that for tachography on the SRF.
I think so. Yes.
Yeah. Is there any other question? Have you ever measured any transient state of enzymatic reaction? If so, which was the rate of one turnover?
We have some data with that we are analyzing. The rate it's let's say it was on the millisecond, if I remember correctly. But there is one point that needs to be addressed and needs to be considered, is that most of this reaction time are of course measured with protein in solution, which might not mean that the turnover is exactly the same in crystal and or in microcrystal. One thing that we are also evaluating is the possibility to cheat with the turnover, in the sense that you can get the crystals in a pH region that is not reducing the efficiency, so that you can slow down the reaction and be able to observe it with more time point. But I think it is also very dependent case to case. Yeah. And also depends if in which way we are going to perform this experiment, because you can think about having a substrate with a cage compound bound but not processing the active site. So in this way, doing a pump and probe experiment so that it makes a clear T0 when the reaction starts. Or you can think about doing a mixing experiment. So mixing experiment, of course, you need a system where the turnover it's slower than the time that it takes the ligand to diffuse inside the crystal. So in that case, sometimes you might want be interested in slowing down the reaction to make it slower than the diffusion time.
One curiosity, when you say slow catalysis, now I'm just rereading your slide. Do you mean something like in the order of the micro to millisecond or millisecond to seconds?
For the tape drive, it has to be in the order for the millisecond to seconds. Yeah. Because this is the physical. I wouldn't say that is a limit, but is a complementarity, because there are some processes that are naturally slow, or that you can slow down artificially. As I said, by working at a different pH or having a less efficient mutants. And it's an intrinsic characteristic of the tape drive, because it's not the fast way to deliver the sample from the mixing, from the time that you mix the crystal slurry with your compound to the time that you do you collect the diffraction images. We are looking for other systems that can complement this time resolution for this kind of experiment on a faster time scale. Yeah, it's for the couple of years for work for the next that we're gonna keep us busy for the next year or so. Yeah, I think.
And if we go back to your screening method, yes, here on the fixed target and foil, if you are coming with your little slurry and you just want to give it a try and see whether the nanocrystal are nano enough for doing the experiments, would you recommend the foil or the chip?
No, absolutely the foil, because let's say the rate of amount of sample by diffraction pattern is higher because of the spacing. So the spacing that we have, I'm gonna turn on the pointer again, On the foils, we can decide the spacing arbitrary. So, and usually with the beam, which is less than 4 micron, we found that 20 by 20 micron spacing in the horizontal and in the vertical is large enough not to get cross-contamination from the previous exposure, and to be able to sample the whole surface, make sure that you don't leave any crystal away. If you use the chip, besides the fact that it can make the experiment a bit more expensive because of the cost of the chip and its fragility, the spacing is given by the chip of the geometry of the chip, which is 125 micron, the distance between two wells. So of course the sample concentration, or the sample density, it's lower in that case. What we are thinking, what we are doing mainly for the chip is to use them for a pump and probe experiment, because in this way you assure that the crystals are compacted and well separated, so that you make sure that when you illuminate with your laser probe, you illuminate only the crystal which you are going to measure, and not pre-activate the neighbor one.
Okay, thank you very much. If there are no other questions, thank you, Daniele. Thank you again. And I would like to remind that next seminar is going to be in 1 month on March the 21st, and it will be the time of ID29, which will be presented. And you have other applause and other thank you from the question and answer. Thank you again. And if you would like to re-listen or ask your colleague to listen to this webinar, it will be in a couple of weeks on the YouTube channel of ESRF. And on that, you can also listen to the ones which have already been, because we're live since November. So there are other 3 beamlines that you can listen to and discover if you haven't listened to us. And with that, I would like to wish you a nice afternoon and see you next month. And thanks again for your participation. Thanks again, Daniele.